So the idea again is that we have this gamma, and why is this gamma a problem? So let's draw again. So let's draw two cases. First, we're going to have a liquid xenon TTC, and then let's have a high pressure xenon TTC. Now, you notice that the dimensions of these two things are different. Why? Because liquid xenon has a density of 3 grams per centimeter cube, and gas at high pressure has a density which is 0.05, if I don't recall, grams per centimeter cube. We have to check the number, but certainly much smaller. Don't give me that number. I'll give you the. Now, because of that, if I want to put a ton, say here, I need a detector of a dimension, which is actually way big, which is bigger actually than a detector that can hold 5 tons here. Right? Now, before we go into more details, why the gamma is a problem in the case of liquid xenon. So, liquid xenon is holding something, a vessel. The vessel is made of copper. Okay? Copper has some radioactivity. Okay? X microbecquerel per kilogram. This is an activity unit. It counts, it will produce in a total number of counts per kilogram of bismuth. Now, this X number, what kind of number can we put there? So, religious wars can be fought on that number. Typical radiopurity that you measure often without much problem is order of 10 microbecquerel per kilogram. This is okay. It's not difficult. You can find that copper without suffering that much. It has to be ultra pure copper. Right? But if we put 10 here, it's kind of fine. Now, by the way, this thing will have, let me call 20 centimeters of copper. These are actual numbers from Nexo. Here actually they have more, even 40, but who cares? 20 centimeters of copper is a big thing like this. So if I'm going to get 20 centimeter copper, and the dimension of this thing is of the order of 170 centimeters by 170 centimeters. So almost 2 meters long by 2 meters wide, a bit less than that. So it's going to be quite a few tons of copper. So can you get cleaner copper than 10 microbecquerel per kilogram? You can. You can do electroform copper. And people have been able to measure clear measurements of electroform copper at the level of 3 microbecquerel per kilogram. Certainly I know that Gerda and Leyen use ultra pure copper at the real limit of the radiopurity in small quantities, very tiny quantities. But let's play the game. Let's keep this as one number and let's keep this other number. So these two numbers, which are apart by a factor of 3, are the difference between being realistic, conservative, and being openly optimistic. Okay? Let's keep these numbers in hand. Now, if you put some activity of bismuth there, and we can plug one number or the other, you end up with a number of decays here. And 1.4% of these decays, 1.5% of these decays, will be a penetrating gamma of almost 2.5 MeV, yes? So these gammas will propagate in all directions through the copper. Yes? Now, let's take a look to this with some detail. This is my copper slab. I'm in a random point, say here. I am shooting gammas 4 pi. Everything that goes backwards, I don't care. So I can make my integral here. So let me just take this point, make an integral 2 pi, and move around this lab. So make, yes?
You said that these gammas are coming from the bismuth's decay, but you're pointing like you showed this emission is coming inside the copper. That's what I don't understand.
It is inside the copper, yes.
The bismuth is inside the
Bismuth
copper.
is bismuth 214. It appears in the change of decay of uranium. So in every material, everywhere, you have tiny traces of uranium and thorium. So the uranium will decay through a decay chain that we can take a look later, and will end up, I think I showed you in the lecture yesterday, we can review that later. So you end up in an equilibrium situation in which all the daughters of uranium are living there. So you have a number of nuclei of bismuth 214. You know, the guy is decaying, but more is coming from uranium. Uranium takes 10 to the 10 years. So you have an equilibrium. You always have the same quantity of bismuth 214 because what decays is being provided by uranium. And uranium you have there forever, yes? So you have a number of atoms of bismuth 214. And the way we express the activity is by giving you the number of decays associated to that. So what you want is to say, okay, I have 10 or 10 microbecquerel per kilogram, which is so many decays, out of which 1.5% are the gamma, so reduce it by 1.5%. Now you need to propagate this gamma. This gamma can be produced here, or here, or here. So, okay, you can make an infinite slab approximation, and then integrate over this distance, m for 4 pi. And you can do this integral analytically, not very difficult, or you can do a little Monte Carlo, not very difficult either. Understand the problem, right? Why do we need to do that? Because we need to take into account self-shielding. So the copper will eat everything that is too far away, and everything that goes to angles too large. And everything that goes backwards is not my problem either. So what I need here at the end of the day, this is my TPC volume. I'm exaggerating the copper. Is how much gammas arrive here. Yes? And for that, I have the ingredients. And the other ingredient that I need is the attenuation length of copper. A number that we will call mu, copper, and which I will provide in a second. Okay? Of course, how do you attenuate? You attenuate following an exponential law, right? So the exponential law of attenuation is going to be E over minus the distance that you go over the attenuation length. And the attenuation length itself is 1 over mu, and mu is the range that you recover. So an attenuation length copper from the top of my head, but wait, that I give you a number. It's an attenuation length of the order of 3 centimeters, if I recall well. Okay? So it means that if I have 20 centimeters here, then I have 7 attenuation length, and this is an exponential. The guys who are back are in there, right? So you need to do this integral, where you need to integrate this as a function of this distance and of this angle. And with that, you get the attenuated flux of gammas in the chamber. Is that clear? Now that you have the attenuated flux of gammas in the chamber, this, by the way, is the same calculation for the liquid xenon TPC and for the gas TPC. Yes? You can vary the amount of copper that you have in each one of them. The dimensions also change, but the calculation of the attenuated flux of gammas is the same. Okay? Now let's think on the liquid TPC. Gammas are coming in, of course, all the angles. Yes? What am I going to do to get rid of them? Well, I am going to remember that liquid xenon is a good calorimeter too. And the attenuation length of liquid xenon is of the order of 8.5 centimeters, which is more than copper, obviously, but quite remarkably small too. So what I can do, suppose that this is a liquid xenon, I can define a porium inside the volume in such a way that the gammas that are coming here attenuate themselves. And so some of them will attenuate and some of them will come. Yes? So my second problem now is to compute what is the fraction of gammas that are emitted here, also isotropically. I'll make it here. Given that I have another attenuation length, another exponential decay, that comes with this. How can I do this calculation? You can do it in a number of ways, but there is a very simple way to do it. Consider 2 cylinders. You have the outer cylinder, you have the inner cylinder. So from each point and any point of your cylinder, you need to compute the rate in which this thing is emitted here and intersects the cylinder. Yes? Sometimes you will intersect and then you have a distance. Sometimes you will not intersect, and then no matter that, this distance, the equivalent, the weight of this is 0. Sometimes it will be in the body, sometimes it will be in the caps. You need to do a couple of different calculations. And if you want to know the effect of these gammas, all what you need to do is to compute the weight of each gamma. So each gamma counts as 0 if it doesn't get into the liquid xenon, and as a weight, which is the attenuation over the length, not the length, the length when it cuts. I have done this, I've been attenuated on average by exponential minus d over a lot, and so I end up with a given weight. So I need to get the average distance that I move here, and then I get the average weight, and then I get the number of gammas that make it inside. Now, we can do quick calculations. Quick calculation is, okay, this is, I'll give you the precise numbers later, which are the ones of next one, but let's be quick. 2 meters. 2 meters. And this one is 1 meter, 1 meter. So the quick calculation is 1 meter, so attenuation of E over minus 100 centimeters over 10 centimeters. Right? So we know what to expect in rough numbers. We should do a quick calculation and say, okay, then rough number should be that, and then we refine our calculation. Understood? Now, we have a number of gammas, effective gammas, which made into my self-shield region. Oh, yes? Now, these gammas of 2.448 interact following the typical interaction. So you have a quantum cross-section and then a photoelectric. In first approximation, I don't give a damn about the comptons. Let me assume that all the comptons will be either out of my energy window or I will see them by separation. Damn the comptons. Only photoelectrics. So I need to know another number that will reduce it is the fraction of the gammas that have made inside that are actually photoelectric cross-section, which is of the order of 1%. So this is another number, 1%. So now I have true gammas of the right energy that have made a photoelectric, therefore, how many? You tell me. Can I do anything else in liquid xenon? For that, we're going to assume two extra things. The energy resolution of liquid xenon, you will see that tomorrow, is something in between 0.7% sigma multiplied by 2.35 and 1.3% sigma, so multiplied by 2.35. This number comes from EXO, and I will discuss that tomorrow. The technique of single phase that EXO uses may be a bit limited in the solution. 0.7 comes from the large dark matter detectors, and they have more light, and they give a very pretty, this is a spectacular number, but still you need to multiply by 2.35. So now you have your signal, which is in 2458, and you have some resolution sigma, called the sigma 0.7, anything between 0.7% and 1.1%. And then 10 kV to the left, you have another Gaussian, which is the gamma, right? And they overlap. How much they overlap? They are separated by 10 kV. Let's see that our resolution is 0.7 times 2.3 would be something like 2% maybe, 1.5%. So this could be, we are at 1% of 2,500 is 25. Let's see that we have a resolution of the order of 40, sigma to sigma, and 10 apart. Not much of a separation, right? But you can do it. You just plot your separation, and now you can say, of course, if I have two gammas, this will be, it's not that useful for liquid, but it will be necessary for gas. If I have, I'm exaggerating now, of course, this is signal, this is background. Now I can choose where my ROI could be this. I can go this. And if my ROI is this, I will take all this gamma background. Yes? But I can choose to take my ROI here. And I will take very little background, but with less efficiency of the signal. So you can play. Now, you can play, and you have more or less freedom depending on the energy resolution that you have. So in the case of liquid xenon detector, we have done. What we have done is to, first of all, compute the amount of gammas that make it inside. Second, propagate the gammas. And third, at the end of the day, put a bit of energy resolution as a separation, which, as you will see, is not super useful unless you manage to get the extreme of the resolution that you think you can achieve. This is the liquid xenon problem. Now for the gas xenon. For the gas xenon, first of all, you have the same propagation problem, but the dimensions are different. Okay? So now the dimensions of your detector are different. It's larger detector. You're going to have more gammas, more surface. And second, the gammas, you're going to propagate them. Now it's a different game. How do you propagate the gammas of the gas? Now, you propagate the gammas of the gas like this. Because there is no inner volume in first approximation. In practice, we are going to put a small fiducial volume. And let's ignore that for that. Now, what we know is that now the gas tends to be transparent. The attenuation length actually in gas at 15, 20 bar pressure is of the, is of the order of 3 meters. So gammas take 3 meters to get attenuated. But of course the detector is of the order of 2 meters. So many gammas get attenuated. So now you propagate the gammas through the detector, you compute the length, okay? And then you weight it again with a much larger attenuation length. But of course now you don't have a self-shielding. So, wow, all of a sudden seems that we are in trouble here. Then, first of all, bigger detector, more mass. Second, not self-shielding. So I'm going to have a huge amount more number than liquid xenon. Why is that so? Because liquid xenon, main idea is I want to approximate myself to perfect shielding. And what I am ready to pay in exchange of perfect shielding? Energy resolution and perfect separation. My energy resolution is good, but not super tremendous. My signal identification for other things is good, because we are just discussing the leading background. But for the photoelectric gamma, 0 signal separation. Because in liquid xenon, the photoelectric gamma looks exactly the same like the 2 beta beta. Now, we are back to gas. We have plenty of gammas interacting. But we have 2 handles now. Handle number 1, energy resolution. So here we're going to use our target number. We can use 1% if you want to, but let's play with 0.5% or with 1. So you're going to tell me what is your favorite number to get some reduction in exchange of the signal. By the way, in this discussion with liquid, we have forgotten the price we pay. Let's not forget that. Look at this detector there. The total volume, I'll give you later the number, but the total volume allows me to put a mass of 5 tons. As you will see when I go to my self-shield volume, 1 ton. So the price I pay for shielding is straight away 80% of my mass, which hurts. Jesus, it hurts. Particularly because my mass is enriching, which is very expensive. So nothing is for free. Okay? Now, once I have paid 80% of my mass to self-shielding, then if I don't want to, or I don't need to do energy resolution, I'm done, basically. If I need to do energy resolution, maybe I need to pay more. But to start with, 20% of the signal. Now, in the case of gas, I am paying basically nothing in this approximation for the fiducialization. I will do something small here, but this is not especially relevant for this count, right? And now I need to pay on the energy resolution. And on the energy resolution, I need, let me assume that I have, do the calculation for 0.5% and do the calculation for 1%. And then you will have different prices to pay in signal to background reduction. This is handle number one. Handle number two, I have my single electron versus two electrons, remember? And I will give you a curve of signal versus background. And then decide where you want to put your cut. Now, how is this curve obtained? Remember that we used to plot the energy of block 1 versus block 2 in the electrons. So the energy of block 1 versus block 2 tends to be here for the signal and tends to be here for the background, right? Block 2 has no signal because there is no block 2. Actually, the modern way we do things in NEX is not doing this pretty scatter plot, but letting a neural network do it for us. Of course, they are smarter than us, right? This has implications. In order to let the neural network do the work, you really need to have a very good description of the data, the color, this and that. But this is why you're going to make physics that will take 5 years of your life, and make you suffer and make you happy, and you will cry about it, and then eventually you will demonstrate the results. Yes? Tell me.
Sorry, but regarding the
Sì.
Nexo or Exo 200,
Next slide. Yes.
there is a possibility to make a distinction between single site and multi-site.
Yes. Yes. But remember, I have already absorbed that in the cross-section. What the photoelectric gamma will only do photoelectric, so not single track. A quantum gamma will do two, and then you will see it throw it away many times. But I already simplified the problem.
No.
So the problem is, this is a very relevant question. The gammas can do photoelectric or Compton. If they do Compton, it's two interactions. And then they can be apart a few millimeters, and liquid signal sure enough sees them many times. And so then you have topology in that way. But I already got rid of that. I am assuming that all the Comptons are gone. Only the photoelectrics. And in the photoelectrics, there is nothing there. Only one interaction. Yes? This is what is pretty about this problem. It's tidy. It is tidy, and actually it's meaningful. Okay? So now we have these two handles. So in the case of NEXT, you can, on the high pressure, you have two curves, or you will produce two curves, and you decide what is your favorite number. Okay? Now, is the problem sufficiently clear and formulated? So I am going to provide in a second, I will send a sample of the files with the numbers that you need, dimensions and attenuation length and things like that. But of course, you can start already writing away your program. I suggest you use a notebook, Python, you can do whatever, you can use Python or Assembler if you want. I want to try to prepare your own notebook in Python. I suggest that you form groups of 1, 2, 3, 4, 5, 6, 7. How many are we? 18 or?
In total, it is 18, roughly
18.
18.
So groups of 3. Groups of 3, that makes like 6 groups. And it's not too much to work. If you make groups of 3, try to not to be a 3-guy working legend. The 38 American, try to make something. Picture. Decide. And then form 6 teams. At least one person per team has a computer that runs Python notebooks. So don't go the 3 guys that general numbers, and you produce a default result. The question that I'm asking, the default question is if we assume the default number, 3 microbecquerel per kilogram, this resolution, this data, how much background from bismuth 214 you will have in these detectors that are ton scale? Okay? If the answer is 1 background, this is bismuth 214. It is a dominant background, but not the only one. There are many others. So this is a best case. If we do the calculation and the answer is 7 events of background, let's go home. Okay. If we do the calculation and the answer is 1 event of background, oh, the guys may have a chance for 10 to the 27, but hardly for 10 to the 28. If you do the calculation and the answer is 0.1 event of background, maybe they can do something. What is the purpose of this? The purpose of this, first of all, that we have a way to quickly estimate. I am not interested about showing you sensitivity curve. My sensitivity curve is better than your sensitivity curve. I'm interested in letting you understand how to do sensitivity curve, which means how much background you have under certain conditions. Once we have the default answer, then we can play. We can change the what happens if the contamination rather than 3 microbecquerel is 10. What happens if the energy solution in X instead of 0.5 is 1? What happens, okay? How much signal I pay for how much background? And at the end of the day, we want to have two sets of numbers, and we want to have an understanding of how these two different techniques, two different ways of doing things allow us to work out this. Any doubt? All right. Since there are no doubts, you take minutes for your teams while I prepare the data and put it somewhere. Okay? The team leader sent me an email saying I am the leader. The leader is the guy to who I will send the data. Okay? And later the address. The problem is already solved. But you don't know where to make it come from. And please don't look for it. It has a very obvious name. Don't do it. Okay? Don't spoil yourself the fact. So, form your groups. In total, for each group for most, send me the emails of the 6 group leaders or the 6 group spokespersons, and then I send you the data. Okay?